All right, everybody. So the problem of the day, we were looking at a hydrolysis reaction. And is this an acetal, a hemiacetal, an imine, an enamine? What would we call this? Could be an acetal. And yesterday I said the key is to find the carbon with both nucleophiles attached, which would be this one. And that's the carbon that was your original electrophile, meaning it was the electrophilic carbon on your ketone or aldehyde. And so we can pretty quickly go through this, but let's do the whole mechanism. So in the first step, we're treating it with acid. So we'll do a protonation, and we'll protonate one of these ether groups on there. So I'll do the full arrow pushing too. Kick off our conjugate base. And then in the next step, we'll shove off this protonated ether. So this is a ring opening. And now this oxygen over here has a positive charge. What would the next step be? Yeah, adding water, right? Because we've got a new electrophilic carbon this water can add into. Kick up electrons. Our water is now protonated. So we need to do a proton transfer, and I'll just show this with the conjugate base, where this conjugate base can come grab a proton off of our water, kick down electrons. And then in the next step, we can protonate our ether again. This time on the other side of the ring. Kick off our conjugate base. This is kind of like setting a mousetrap. You're making a very, very high energy intermediate so that you can kick it off. So now the oxygen nearby can donate its lone pair down and then kick off this ether group. And let's see. Now we're almost there. The very last step will be our conjugate base, deprotonating the proton up here, kick down electrons, and we get to our final aldehyde. And I'll draw in the hydrogen just to emphasize the fact that it is an aldehyde. So if you are having trouble with these reactions, one thing I really recommend doing is practice doing an imine formation, an acetal formation, an enamine formation, and then try to do it backwards and do the hydrolysis reaction and then practice that a few times. I know there's a lot of these in saplings, so those are really good to work on. What a lot of people are doing that I really like is they keep a pad of paper next to them when they're working on sapling problems, and they try to hand draw the full mechanism rather than just brute force memorizing their way through it. It's a lot easier if you can work through a mechanism, especially if you're encountering an unfamiliar problem. Yep?
Instead of the ketone there, could you install an alcohol for a water molecule dehydrated and make 2 alcohol groups there?
2 alcohol groups off of the aldehyde?
Yeah, so instead of the aldehyde, make it 2 alcohol groups coming off of that carbon. Like, see where you have.
Oh, so you're talking about forming the hydrate.
Yeah.
So we could do the hydrate formation. When we covered hydrates, we said that they aren't favored typically in a very high concentration, but you can imagine this going even further and forming the hydrate and having two alcohols coming off of this central carbon and not having that carbonyl. It's just going to be a very, very minor product. That's a good point. All right, so now let's go back to chapter 20, and we're almost done with it. This is one of the beefiest chapters in the book. And we only have 2 more reactions out of the 15 that we've learned in this chapter.
Oh my God. Why did you say that?
All right, this next reaction is pretty neat. It's called the Wittig reaction. If you hear somebody pronounce it Wittig, you should slap them and say, no, it's a V. He's German. It should be Vidiq. He won the Nobel Prize in 1979, George Wittig. And this reaction was one of the more modern ways of installing a carbon nucleophile. The other ones that we've seen were Grignard reactions, which we said suffer from a lot of problems because they're very strong bases. And then cyanohydrin reactions, where you're dealing with cyanide, also not the friendliest reagent. The Wittig reaction is much more friendly to do. And the overall reaction is pretty straightforward. It looks scary, but don't let it intimidate you. So you start with your ketone or aldehyde. And then you react it with this phosphorus reagent with 3 phenyl groups coming off of it. And then you can react it with a carbon. Actually, let me change the colors here. Carbon with either 2 hydrogens or 1 R group, like an alkyl group, and another hydrogen. And this has a lone pair with a negative charge. And your phosphorus has a positive charge. So that carbon, because it has a negative charge, is very, very nucleophilic. This is called an ylide. And we'll go through the mechanism for the formation and preparation of ylides. But the final product of this reaction is a new alkene. So you can start with an aldehyde or ketone, react it with an ylide, and you get an alkene. And normally with these alkenes, when you form them, you get the Z isomer, not the E isomer. However, there are a few variations on this reaction where you can favor the E isomer over the Z and vice versa. And there's a whole bunch of modifications. There's one called the Schlosser modification that you can use to get the E. We're not going to get into regiochemistry that much. As far as we are concerned, you normally get the Z. All right, now let's go through the mechanism. First, we'll go through the preparation of our ylide.
It's going to be long, kind of?
Yep.
Okay. We're getting a fresh piece of paper out and
Fresh one. There we go. All right, so the ylide is that carbon nucleophile that I have drawn above the reaction arrow. And the preparation starts out with triphenylphosphine. And I'm not going to draw out the benzene rings. I'm just going to abbreviate them as pH. And then you react this with an alkyl halide. Actually, let me move this up a bit. And so the phosphorus lone pair can attack our carbon, kick off our leaving group. Yep, it's just a normal SN2 substitution, right? And now you end up with 2 hydrogens and an R group. And then your X minus over here. Can we use a tertiary alkyl halide? No, why not? Yeah, exactly. So for these reactions, one important thing to note is that it works best with methyl groups. Oop. Or primary alkyl halides. You don't typically see this done with a secondary alkyl halide because SN2 substitution is just too slow with secondary carbons in that position. All right, now the next step, we're going to take a lithium reagent. This is called butyl lithium. Which is a very strong base. So I'll just abbreviate this BULI from now on. And what this will do is come grab one of these protons off of the carbon end, dump down electrons onto the carbon, and we've got our hydrogen on there, and we've got an R group, lone pair with the negative charge, and a positive charge on our phosphorus. Looks pretty unstable at first sight, but why is it a surprisingly stable carbanion? Resonance, right? So we can draw both resonance forms. Phosphorus is a very weird atom because it's lower on the periodic table. It doesn't follow the octet rule in the same way that we're used to seeing. So you can draw these in both forms. With nitrogen instead of phosphorus? No, nitrogen's higher up on the periodic table, and you don't see pentavalent nitrogen really at all. I can't think of any examples, but you do see phosphorus where it's shown with more than an octet. And we're not going to really get into that, but there's some weird chemistry going on there. They're not true 2 electron bonds at that point. All right, so on the left, this is called a phosphorane. And on the right, this is our ylide. Oftentimes, people call the ylide just the Wittig reagent. From here on out, I'm going to primarily just stick with the ylide form because it's much easier to see where the nucleophile is on the carbon if we're drawing it using that form. Are there any questions with the formation here? One important thing is sometimes people will draw this as a one-step process, meaning you throw in your alkyl halide, the triphenylphosphine, and your base all in one pot. That won't work. It's always 2 distinct steps, so you should always, with your arrow, have one and then include your alkyl halide, and then a second step that's the addition of your butyl lithium. These are always 2-step reactions. All right, now let's go through the mechanism. So I'm going to choose just acetone as our generic ketone or aldehyde. It doesn't matter what sort of ketone or aldehyde you use.
Is this one really stuffy?
No, it's not. And then we've got our ylide over here. The phosphorus has a positive charge. I'll draw in our hydrogen and our R group. And then our carbon has a negative charge, right? So we've got our ylide and we've got our ketone. And so we can show our nucleophile on our carbon attacking our ketone and pushing electrons up, just like we saw in our others. And this reaction is reversible. Let's see, so we've got our carbon here, we've got an R group, we've got a hydrogen, we've got a phosphorus with 3 phenyl groups coming off of it. Okay, and what this is called is a beta-ene. What do you think happens next? We've got a negative charge right next to a positive charge. They're just going to bond. Because they're in such close proximity, this is an unusual situation of forming a 4-membered ring. It just hops over. I have always pronounced it beta-ene. I'm sure other people pronounce it differently. Let me draw this a little bit more clearly. All right, and this is called an oxaphosphatane.
Yeah.
It may show up on saplings, so I want to make sure I get them down.
Well, as long as you're not gonna be like, what is this?
I'm going to ask you to spell it forwards and backwards,
Yeah. Yeah. Well,
while on your head doing some sort of arithmetic problem on the side.
Yeah.
All right.
I wouldn't put it past you. Yeah, me neither.
And then the next step in this reaction, let me actually show this bond more clearly. These bonds will break and jump over.
What causes it to break?
Primarily ring strain. 4-membered rings aren't very stable. And then I'll talk a little bit more about another major driving force for these reactions. So the main product that we're interested in is our Wittig product. So we formed our alkene with our Vidiq.
I have to slap you if you keep pronouncing it Wittig.
See?
You told us to.
I know. It's my pet peeve.
Funny, that's the only thing.
And then our byproduct for this reaction is triphenylphosphine. Oxide. Triphenylphosphine oxide is like forming a rock. Once you make it, it's very, very hard to unmake. And so this is a thermodynamic driving force. And in fact, I'm going to go back and redraw this as a single-headed arrow. Sorry. Because this is a thermodynamic sink. And in this case, it's irreversible. If you go on and take more organic chemistry, you'll see phosphine oxides over and over and over again, because a lot of people, I wouldn't say stole his idea, but they borrowed it as using this as a major driving force for this reaction. It's a similar idea with our last problem of the day, where we formed something that was aromatic, and that last step was irreversible. This last step is also irreversible, and we're able to form our alkene. And like I said, the alkene is normally our Z alkene. Oftentimes you get a slight mixture of E in there, but the predominant or major product is going to be your Z alkene. All right, so now let's go through some practice problems and try to plan our route, because this does get a little confusing. Oh. So let's take this example. There's one I pulled from the book. And we have to figure out how to make this alkene. In particular, we've got to look at this double bond. Let's ask ourselves, how do we make this? And we just talked about using the Wittig reaction in order to make this. But the question is, did the carbonyl carbon come from this carbon? Or did the carbonyl carbon come from the other carbon? We've got two different options available to us. So let's break down the two options. And with option 1, we could say that it came from that leftmost carbon, meaning our aldehyde would look like this. And then we would need to react this with some sort of ylide reagent. So we could combine both of these together and perform a Wittig reaction. Alternatively, we could take that rightmost carbon. We could say, well, what if that was our carbonyl carbon? And if we do that, then our ylide needs to be slightly different. Oh. And then we would react this with a cyclohexanone reagent, and again perform a Wittig reaction. So we've got two options available to us. Question is, which one is better or preferable? What do you guys think?
How do you even tell?
One on the left, because it's a primary carbon, that would be a second.
Well, now let's go and look even back one step further. Back when I was talking about preparation of the ylides, we said it works best when you have an either unsubstituted ylide, meaning that R group could be a hydrogen, or at the very most one alkyl group. Because we said SN2 reactions with an alkyl halide proceed much, much faster for methyl and primary than secondary and tertiary. So if we go back and we look at our two different routes again, this one's going to be very hard to make. Whoop. It would require a secondary alkyl halide. What's that? Yeah, so if we look at this phosphorus ylide, it has two R groups coming off of it. You don't typically see these because they're very, very hard to make. But if we look at this one, this carbon only has one R group coming off of it. It doesn't have two. The other substituent is a hydrogen. So in this case, we're able to make that because it would require a primary alkyl halide to make, not a secondary alkyl halide to make. So we could say would be easier to make. And then I'll say only needs a primary alkyl halide. All right, so now let's go through and draw the full scheme for this reaction, specifically saying that this route on the right is our better route because it's easier to make our ylide reagent. So let's go back and see how we would make our ylide reagent. So I'll call this our scheme. So we've got our primary alkyl halide. What's our first reagent that we add? If we're going to make our ylide?
C, carbon, or the whole side.
Yeah, we've got to add in our triphenylphosphine. So that's our PPH3. And then what's the next step in order to get to our ylide?
What?
Butyl lithium.
Yeah, I said it back.
So we'll call that BULI. And now that we've done that, we can create our ylide. And then in our next step, we can just throw this in with cyclohexanone. And we're able to get to our final product.
You're going to do a mechanism?
Do you guys want to see the full mechanism?
I do. It helps me understand it.
Is it important on the test?
I will ask you to show a mechanism
The
for
full mechanism?
yep, for everything I've shown.
Will it show us the mechanism?
All right.
Well, wait a minute. If you're not going to show us the mechanism, then why would we be tested on it?
No, we already went through the mechanism, but let's do it for this specific example.
Oh, okay. I was like, wait a minute.
Yeah, that's what I
what?
was saying. It's like,
Okay, yeah, please. I'd like to see.
So our carbon nucleophile can add into our ketone. So we've got PPH3 plus, and this hydrogen is sticking back. So this is our beta-ene that we were talking about. Now the oxygen will attack our phosphorus.
It's supposed to be equilibrium arrows.
Yeah, they should be equilibrium arrows. Sorry. The first step, because we're using such a strong base, you can show that as a one-way arrow. All right, so now we've got our oxyphosphatane. And this last step we said is actually one-way arrow because we're snapping off that triphenylphosphine oxide. And we're able to get to our final product. So this is one of the few reactions where you see a four-membered ring as an intermediate, but the driving force is the formation of that triphenylphosphine oxide. All right, let's go to our next reaction, and then if we have time, we'll jump into some practice reactions that involve both of these. But I just want to make sure we have enough time to get through the last one. And this is the Baeyer-VIlliger oxidation. And again, this works well with aldehydes and ketones. And the reagent that we use has a very, very unstable oxygen-oxygen bond. Does anybody remember what these are called? It's a peroxy acid. So it's in between a peroxide and a carboxylic acid, so we call it a peroxy acid.
When did we talk about that?
You remember MCPBA?
Yeah.
That's another peroxy acid. So these are used in forming epoxides. And what we get is an inserted oxygen. So if you're starting with an aldehyde, meaning one of those R groups is a hydrogen, what sort of functional group can we make if we're inserting an oxygen? So let's imagine this R group on the right is a hydrogen and we insert an oxygen up in there. We can get a carboxylic acid this way. If it's a ketone and we insert an oxygen, what are we going to get? An ester. So it really depends on what your starting material is. If you've got an aldehyde, you'll go to a carboxylic acid. If you've got a ketone, it'll go to an ester. So now we've got a new set of functional group transformations available to us. All right, let's go through the mechanism. It's only a 3-step mechanism, but it's a little confusing.
What's new?
All right, so let's take our generic ketone. I'll just use acetone. And we're going to react this with our peroxy acid. The first step is this terminal oxygen on the peroxy acid will act as our nucleophile and add in. Kick up electrons onto that oxygen. Now this oxygen has a negative charge. And the oxygen that added in has a positive charge. So now we'll do a proton transfer.
Why don't they want to hook up?
Because in that case, you'd have two oxygens colliding into one another, and you'd be forming a 3-membered ring. Oxygen-oxygen bonds are very, very unstable. So in this case, this will actually occur through an intermolecular proton transfer because we're going through a 5-membered ring, which is a little bit more favorable than a 4-membered ring. Or I should say a lot more favorable than a 4-membered ring. So now that oxygen has a positive charge. And now the weird thing is, I'm going to draw in this full CH3 group now. This will actually hop over. And what we call this is an alkyl migration. So this entire CH3 group is going to hop over onto that oxygen. This bond will hop over, and this bond will pop over.
How come it doesn't ever do that with other bonds?
We've seen alkyl migrations with methyl shifts.
Yeah.
This is
Different.
kind of like a methyl shift.
Not really.
No, up to just make it up
Not always.
sometimes.
And then, oh, I forgot an arrow too. So this clamps down, which helps promote the alkyl shift. And then that whole methyl group will hop over onto that oxygen.
Reversible.
Oh, this should also be a one-way arrow. Excuse me. So now if we look at our original ketone, it's now become an ester. And let me actually draw it in a specific orientation. The new group that we popped off is a carboxylic acid. So our main product is the ester, and then we get a carboxylic acid byproduct. So let's go back to this part right here. This is an alkyl group migration. And some alkyl groups love to move. Other groups want to stay put. They're not happy moving. And so we can experimentally test which alkyl groups like to move the best. And the most common one is a hydrogen. So we've seen hydride shifts before. Then the next one is tertiary. Then the next one is secondary, which is about tied with a phenyl group, which is better than a primary, which is better than my example of using a methyl group. If you force it, you can get a methyl group to go, but if it has an option, it would rather go with something like a hydrogen over a methyl group. So this is the overall trend. So the key thing to look for is, do you have any hydrogens or do you have any tertiary positions? And then use this list of trends to figure out which would be your preferred migration. So let's go through some examples.
Why is it the hydrogen's the most, like, wouldn't it be closer to the methyl since it's so small?
That's a good question. And in this case,
Because it just seems
I-
so out of order.
I don't have a good answer. This is what's just been experimentally shown.
Okay.
I'd have to do more digging to find what's going on. Okay, so let's take some examples. And we're going to pick which side is going to be the migrating side. Okay, so we're going to do a Baeyer-VIlliger oxidation on cyclopentanone. Is there one side that's more substituted than the other?
Yep.
No, so it doesn't really matter, but we're going to form an ester. And the reason I wanted to bring this up is that this is a unique type of ester. It's an ester in a ring system. And these are called lactones. Lactones are found in a lot of drugs. A lot of pharmaceutical ingredients go through lactone derivatives. They're also very common in the plastics industry as well. So you can imagine you can ring open a lactone too. So we have a hard time ring opening a ketone or aldehyde when it's in a cyclic system, but by turning it into an ester, you've turned one side into a better leaving group and you can pop it open. So that's one example. Let's do another one. Are we going to get an ester or a carboxylic acid? And why is that? Because it's an aldehyde and the hydrogen is more likely to migrate than the primary alkyl group. So whenever you're looking at these, you can say this one is more likely to migrate. All right, let's do another one. Now we've got a ketone. We're going to react this with a peroxy acid. Question is, what ester will we get? Will the oxygen get installed on the left side of the carbonyl or the right side? Left side. Because if we look at this side is more likely to migrate. So if we look at our final product, we'll have an isopropyl group coming off of our ester. So it is a kind of bizarre mechanism, but it is pretty functional for turning what used to be not a very good leaving group into a good leaving group. So we could pop off the ester if we wanted to.
Okay,
Yep.
what if you had a phenyl and a secondary one on the same thing?
Oftentimes you would end up with a mixture of products. It'd be very hard to control. If one's not highly favored over the other, you just end up with a mixture. Yep. All right, so with our remaining 5 minutes, I thought we would go back and do a couple practice problems from our Wittig reaction. Oh. And these will be kind of fill in the box sort of practice problems. On the left side, I want you to give the alkyl halide. So I'll include a box for your alkyl halide. And then the reagents we need in the first step are triphenylphosphine. Oop. PPH3 followed by butyl lithium. And then I want you to give the illid.
Okay, I will say you only give us one than
I'll help you guys. And then over here you need to give your ketone or aldehyde. And then for this example, our product is going to be this alkene. So we need to figure out what all the reagents would be that we need for this reaction to occur. So I'll give you guys a minute to work on this, and then try talking with your neighbor and see if you guys agree. It might help if you go back to the example methodology we did where we looked at our two options.
before the product, we have that grain thing.
So I'm not going to have you show the full mechanism. We just want to know the reagents right now. So let's break it down and work a little bit backwards. And I'll give you guys two options for your ketone or aldehyde. Our first option would be to have cyclopentanone. Our other option would be to have our aldehyde. Which one do you think is the better option? So remember, our ylid we want to be as least substituted as possible. So knowing that, we want our ketone to be the most substituted, right? So if we think about it, this would be the better route. So we can cross out the other one because that's the more substituted carbonyl. It's got two alkyl groups coming off of it, so it's taking the majority of that. So the question is, what ylid would we need to react with it? We've got our triphenylphosphine with the positive charge. What's the carbon nucleophile that's attached to it? Yeah, it's an ethyl group, really. So we've got a CH3 and a hydrogen. So that's our ylid. So that ethyl group essentially got added on right there, right? The question is, what alkyl halide would we need in order to make this ylid? There's a lot of... Anybody? An ethyl halide, right? So we could just arbitrarily say maybe ethyl bromide. You guys want to do it? Or actually, we're running out of time right now. We'll do another practice one at the start of class tomorrow. But the key is, with a lot of these, work backwards. Try to make your ylid as unsubstituted or least substituted as possible, and then work backwards through these.